Welcome to this explainer. So, I was recently looking into exactly how rockets manage to land themselves. And honestly, the mechanics behind it are just absolutely mind-blowing. We're going to start way back with 17th century physics, the basic concepts that even get us off the launch pad in the first place, and then travel all the way to the cutting-edge artificial intelligence that's literally teaching spacecraft how to land on the moon unsupervised. It is a fascinating journey, so let's jump right in.
Okay, let's dive into this. Why does reusability even matter? Well, just look at these numbers. According to NASA, a single launch of their single-use space launch system, or SLS, costs upwards of $2 billion. $2 billion! On the flip side, SpaceX is developing Starship to be fully reusable. Their ultimate goal? Bringing that cost down to around $2 million a launch. That is a massive 1,000% cost reduction. I mean, this is a real game changer. This is what's eventually going to make space travel and space-based technologies accessible to all of us. But to fully grasp how humanity is pulling off this mind-blowing economic shift, we really need to build and fly a rocket together, step by step.
Here is our roadmap for today. We'll briefly cover the physics of flight, the anatomy of a rocket, how we power the engine, the reusable rocket revolution, GNC systems, and finally, AI and the future of landing. All right, let's blast right in.
Section 1, the physics of rocket flight.
To really get modern rockets, we actually need to time travel back to 1687. That's when Sir Isaac Newton published his laws of motion. This right here is the absolute bedrock physics that makes getting off the ground possible. Specifically, we're talking about Newton's third law. For every action, there is an equal and opposite reaction. Think about riding a skateboard. If you're standing totally still on the board and suddenly jump forward, what happens? The skateboard responds by shooting backward in the exact opposite direction. Well, a rocket works in exactly the same way. The engine aggressively pushes hot gas out the back, and in return, that gas pushes the rocket forward. Or, as the everyday astronaut casually sums it up, the goal is really just to throw stuff out the back as fast as possible. Now, what's really fascinating here is that because rockets rely entirely on this action and reaction of gases, they actually work way better in the vacuum of space where there's no air friction slowing them down. But getting up there means they have to move incredibly fast. To completely escape Earth's gravitational pull and travel out into deep space, a rocket has to hit what's called escape velocity. That is a staggering 40,250 kilometers per hour. Just let that scale sink in for a second. That is fast. Let's move to Section 2, Anatomy of a Rocket, and see how this builds together. Taking that abstract physics and turning it into a physical machine, it turns out a rocket is basically just four main systems. You've got the structural system, which is your frame, and that ultra-lightweight skin holding the whole shebang together. Then there's the payload system. This is the whole reason we're doing this, right? It's the satellites, the cargo, or the crew. Next is the guidance system, packed with all the sensors and computers needed to steer the vehicle. And finally, the propulsion system. This is your engines, the tanks, the propellants, and it's absolutely crucial to note here that the propulsion system takes up the vast majority of the vehicle's total mass. Moving right along to Section 3, powering the rocket engine. So how do we actually generate the crazy amount of power needed to get off the launch pad? Well, there are a bunch of ways to power a rocket engine. On the highly simplified side, you have a cold gas thruster. This is wonderfully basic. It literally just opens a high-pressure valve on a tank of gas, like nitrogen, letting all that stored pressure escape out of a nozzle to create thrust. It's super reliable, sure, but not very efficient. If you want a lot more power without getting too insanely complex, you step up to a monopropellant system. Here, a liquid propellant gets forcefully pushed through a catalyst bed, which is basically a layer of reactive materials, and that sparks a very violent chemical reaction. This generates an enormous amount of raw heat and pressure, drastically bumping up the engine's efficiency compared to just using cold gas.
Which brings us to Section 4, the reusable rocket revolution.
Imagine putting all that massive power and engineering together just to chuck the whole rocket into the ocean after a single flight. That is exactly what makes space travel so painfully expensive. But fixing it, reusability, is incredibly tough. Because, there are no gas stations in space. A rocket has to carry every drop of fuel for its entire journey from the second it leaves the pad. And this brilliantly illustrates the infamous rocket equation. Imagine driving your car, but you have to tow a gas tank the size of a semi-truck just to move a couple of passengers. Literally, most of the fuel you burn is used purely to lift the massive, crushing weight of the fuel itself. Because of this punishing equation, reusability demands a massive trade-off. Think about it. To land a booster, you have to carry extra fuel, heavy landing legs, and extra control systems all the way up into space and then all the way back down. For a reusable SpaceX Falcon 9, this means sacrificing up to 30% of its payload capability just to carry the hardware and fuel it needs to return home. 30%. It's a huge penalty, but economically speaking, it is absolutely worth it.
Now, what's really interesting about this slide is the return trip. It is an absolute aerodynamic nightmare. When that rocket booster is falling back to Earth, it's essentially just an empty hollow tube, but with incredibly heavy engines sitting all the way at the bottom. As the quote hits the nail on the head, trying to fly that thing with the heavy engines at the back is exactly like trying to throw a dart backward. It is completely aerodynamically unstable. It desperately wants to flip around in the air. So how on earth did they manage to land it?
That takes us to Section 5, Guidance, Navigation, and Control.
You'll often hear the acronym GNC, but this isn't just some boring aerospace jargon. It is a high-stakes, split-second survival checklist for successfully landing what is essentially a falling 15-story building. GNC breaks down into 3 very distinct steps. First up, navigation asks, okay, where am I and how fast am I moving? Second, guidance asks, where am I going and what exact trajectory do I need to take to get there? And third, control asks, how do I physically steer the hardware to execute that exact trajectory? And the rocket's flight computers are constantly cycling through this loop, reassessing data fractions of a second at a time for the entire descent down. To answer that very first question, where am I, the rocket uses multiple sensors. It relies mostly on GPS and something called an IMU. Now, GPS gives the rocket a general sense of its 3D position using satellite signals, which we all know. But the IMU, or Inertial Measurement Unit, that is fascinating. Think of the IMU like a kidnapped person locked in the trunk of a speeding car. Stay with me here. They can't see the outside world at all, but they can physically feel every single sudden acceleration, every hard brake, and every sharp turn. By measuring those physical forces, the IMU tells the rocket exactly how its attitude and speed are changing in real time. But here's the catch. Literally, all sensors have errors. For example, GPS radio waves actually get bent and refracted by the Earth's atmosphere. It's exactly like how a straw looks totally bent when you drop it in a glass of water. So how do engineers solve this? To figure out the absolute objective truth, the rocket uses a Kalman filter. This algorithm is honestly brilliant. It constantly looks at where it expects the rocket to be, compares that against the slightly flawed GPS and IMU data, mathematically filters out all the noise, and calculates the absolute most highly accurate position possible. Okay, so once it knows exactly where it is, it has to decide how to steer. And here's a crazy fact. SpaceX actually aims its returning rockets to completely miss the drone ship by default. No way, right? But this ensures that if the engines fail, the rocket just crashes safely into the ocean instead of obliterating their incredibly expensive ship. It only diverts to the landing pad at the very last possible second. But calculating that complex diversion trajectory, that's a massive math problem, and it has to be solved instantly. So engineers use convexification. It's basically a very neat mathematical trick to approximate the problem so the flight computer can solve it in a matter of milliseconds. The computer then uses control hardware, like those waffle-looking aerodynamic grid fins and thrusters, to physically steer the rocket to a pinpoint touchdown. And finally, Section 6, AI and the Future of Landing.
So the crucial point is, we've kind of mastered landing here on Earth using GPS and grid fins. But what happens when we head to the moon or Mars? Places where there is zero GPS, no drone ships waiting for us, and honestly, no atmosphere for grid fins to even push against. Well, researchers at the University of Arizona Space Systems Engineering Lab are literally teaching neural networks to land spacecraft completely unsupervised in uncharted territory. First, they use a 3D program called Blender to create these highly realistic ray-traced simulations of the lunar surface. Then, they use a machine learning model called semantic segmentation to look at camera images and instantly separate the safe, flat terrain from hazardous craters and giant boulders. Finally, they use reinforcement learning to train an AI agent over countless simulations. Basically, the AI learns, entirely on its own, how to process a sequence of camera images and perfectly adjust the rocket's thrust to safely land in a hazard-free zone. It is essentially teaching a computer to see, think, and fly all by itself. And that brings us to the end of our explainer today. We have gone from Sir Isaac Newton's fundamental laws of motion in the 1600s all the way to deep reinforcement learning aiming for pinpoint lunar landings today. But I really want to leave you with a final provocative thought. By mastering everything from propulsion to artificial intelligence, we are actively driving the cost of spaceflight down to unimaginable levels. So, what on earth will humanity build? Factories? Whole cities? Entirely new worlds? What happens when the cost of accessing space simply becomes equivalent to booking a commercial airline flight? Thank you so much for exploring this with me today. Keep asking those big questions, and as always, keep looking up.